All right, chemists. So take two. So back from yesterday, take three. So we expected from a Lewis structure that ozone would have one short bond and one long bond. Turns out that the bonds in ozone are both of equal length. So how do we describe that? Oh, come on, don't play me. All right. What's going on? Resonance. So, oops. Sorry. This. Oh my god. All right, sorry guys. Tech difficulties. I know it's brutal. All right. All right. What's going on? Resonance. So, in some molecules with very specific properties or very specific bonding, electrons can become, we call them delocalized. Generally this is in, generally with molecules that have a double bond or double bonds that can be placed with different atoms. So when you have these molecules that have double bonds that can be placed with different atoms, that means a single Lewis structure is insufficient. So you will need to draw more than one Lewis structure. I'm going to shorten Lewis structure to LDS. So the molecule exists as all structures at the same time. So think of it as like a blend of all those structures. Yeah, and I'm sorry that my handwriting stinks. If you need me to clarify anything, please just ask. I understand. All right, does anybody need me to wait? All right. Yes. Okay, the question is there a way to draw a single Lewis dot structure from a molecule with resonance? Yes. There is a notation for that. I will show you one on the next slide, and then we'll leave it at that. I want you to be able to do the both. All right, are we good? Okay. So, as I said, when is there resonance? More than one place for a double bond. And later on, we're going to, I think it's either next chapter or the chapter afterwards. It has to have pi bonding. So we're going to talk about sigma and pi bonding, but when we have resonance, we have what's called delocalized pi bonding. So we'll come back to that in the future. Just giving you a little sneak preview. So let's go back to ozone. You can draw ozone like this. Or like this. So these are the two Lewis dot structures for ozone that are possible. It doesn't exist as either of these. It exists as a hybrid. I don't want to call it a hybrid because that exists as a combination of both. So instead of having a single bond and a double bond, the bonds act like they're 1.5. So each bond has some of the characteristics of a single bond and a double bond. So it's not as long as a single bond, but it's not as short as a double bond. It's not as strong as a double bond, but it's not as weak as a single bond. Yeah, Wesley. So the question is, what do the pluses and minuses mean again? Those are the formal charges. All right. So what's actually happening here is it's not either of these things. This double bond is actually spread out over the whole molecule. It's not flip-flopping between the two of these. That's not what's happening. It's not going from one to the other and back and forth and back and forth. It actually exists as both of them merge together at the same time. Yep. Formal charges. So the question was, if we don't explicitly ask you to include formal charges, should you add them? We will explicitly ask you when necessary. Yes. Okay, so the question is, with the resonance structure, how do the formal charges work? Well, formal charges are just they're sort of like bookkeeping for us. So it would actually have neither of these. It would just be spread out. It wouldn't be a plus and a minus. It would be spread out over the whole thing. So probably the most famous resonance structure. Somebody shout out a color. I heard blue first. All right, is for benzene, which is C6H6. So benzene is a carbon ring like this with double bonds between every other carbon. Yeah, ugly. So because of the resonance structures are very stable because it has to do with the delocalized pi bonding that we'll talk about. This isn't magic. A lot of you guys still used magic on the test. So like a full octet is especially stable without explaining. Don't use magic. A full subshell is more stable than a partially filled subshell. Don't use magic. Explain. So this gets to Ben's question. Is there a way to draw this? The way you're going to see benzene written in textbooks is this. Or you might see it like this. Generally this, though. Generally this one is the one you... Oh, wait, that's confusing. So the question was, what about the H's? Mr. Hamill will lecture about why the H's aren't there towards the end of chapter 5. No, they are there. The H's are actually there, but we just don't draw them in. And he'll explain to you why that is. Yeah, Thomas. So what does it mean to be delocalized? We're going to talk about that more, I think, in chapter 6 or 7. But it just means that there's not like a single bond and a double bond. This double bond is sort of shared between the two. So it's not central to in between two atoms. It's delocalized and spread over a couple of different atoms. And it has to do with the shape of the orbitals, which we'll talk about later. Yeah. So the question is, my drawing at the bottom right-hand corner of the screen works for an aromatic ring, but not for ozone. We don't need to worry about there might be, but I'm not sure what it is off the top of my head. Like a single structure. So you would draw both. We're going to ask you to draw both resonance structures, or as many as you can come up with. All right. So this is your introduction to resonance. We're going to go delve more deeply into it when we talk about hybridization. But you should just be able to recognize, okay, there's more than one place that I can put this double bond. So there might be multiple structures that I have to draw. All right. Does anybody need me to wait? Okay. Polyatomic ions. Molecules, entire molecules can gain or lose electrons. So we're not just thinking about like sodium losing an electron or chlorine gaining an electron. We're talking about molecules of 2 or more atoms put together gaining 1 electron or gaining 2 electrons or 3 or losing 1. So where you're going to see this the most, and I left a little note for you, and where this is sort of really important in most people's lives is biochemistry. Many of you will take biochemistry in college. I actually wish we had a biochem course here. In our bodies, a lot of things exist as polyatomic ions. Amino acids. Did you guys, those of you who took AP Bio, did you talk about protonated or deprotonated amino acids? Maybe not. No. Not in those words. Okay. So you can have amino acids that have a positive charge or a negative charge. Proteins tend to have like large amounts of negative charge or positive charge. I think it's generally negative charges. So you can have these big molecules that have gained or lost electrons. And in biochemistry, that becomes really important because it changes the way your molecules act in your body, right? Or in nature. So in order to draw Lewis structures for polyatomic ions, it's best to use count and check method. And then formal charge. Okay. So I'll do the first one, and then I will ask you guys to do the next. OH minus. So why do we need the count and check? Well, we have an extra electron. So how many total electrons do we need to draw? Oxygen brings 6 to the party. H brings 1. But now I have an extra one. So how many total is that? 8. So I draw my O bonded with my H. H doesn't need an octet. I fill up my O. Draw. And then check. I have 8 out here. 2, 4, 6, 8. That's what I should have. I'm done. You will see this drawn like this, with brackets around it and a negative sign on the outside. And you can see where that negative charge is, though, if you use the formal charge. So what you actually get is this. And somebody shout a color. Green. The sum of your formal charges equals the charge of the ion. So here, I have one negative formal charge, which is equal to the charge of my ion. If I have 2 minus, then the sum of my formal charges has to be negative 2. Try Cn minus at your tables while I take attendance. Oh, now I lost count. I was counting. Yep. 2, 3, 4, 3, 8, 12, 16, 20, 23. Everybody's here. All right, and we're just going to take a walk around, see where people are at. All right, so if you do this out, you should find that you get this as your Lewis structure. So 2 is draw, 3 is check. So 10E minus, check. Now, where is the negative form? Oh, yeah, go ahead. Do you have to, you do not need, the question is, do you need to write all the steps? You do not need to write all the steps. I'm just doing that to help us walk through. Where's the negative formal charge? Or is that do you have another question? Yeah, go ahead. So if you did it that way, carbon doesn't have the statement was drew it with 2 pairs on the N and a double bond between the C and the N. That way the carbon wouldn't have the full octet. All right. So where is the negative formal charge? On the C. So C, if we remember from yesterday or previous lecture, formal charge is equal, we'll just do carbon, 4 minus the electrons in a lone pair, which is 2, minus the number of bonds, which is 3. So that's minus 1. So that's my polyatomic ion. Yeah. So the question is that considered a coordinate covalent bond? I don't think so, because I think you could make the CN structure with 3 bonds and just have 1 electron on C, and then the C just grabs an electron from something else. So it wouldn't be considered that. But you still have a formal charge on this. Yeah, Griffin. You do not need to circle the extra electron. That's what your formal charge tells you, right? It tells you where the extra one is, essentially. Okay, let's try a tougher one. CO3 2 minus. Give it a go. You know, you guys can talk to each other. It's good to share ideas. Okay, so as I'm walking around, I see some people getting it. So let's just countervalence electrons. 3 times 6 is 18, plus 4 is 22, plus 2 is 24. Is that right? So if I draw this out, COO, and I count that all my octets are full, but I think I have too many electrons there, right? So what I'm going to do is say that's not right. And now I'm going to make a double bond. Oh, and there we go. That has 24 valence electrons. All the octets are full. We're happy. Now my question is, what about formal charges? I want people to think for a second. Where would the formal charges be on this polyatomic ion? You know, I'm going to get more voices involved. Whoa, I haven't. Oh, I didn't switch it from the beginning. GG. Okay. Yep, C definitely has 0 formal charge. Okay, so what do you know that the total formal charge needs to be? 2 minus, right? So I have 3 oxygens. Chances are, which ones are they on? It's okay. Don't feel any pressure. We're all in this together. The ones with more unpaired electrons. Good. So the formal charges are on the 2 oxygens that are singly bonded, right? So this is what it would look like. Now, I had a question come up over here that was, do you want me to draw the others? Now, what does that mean? Great question. What does that what could that possibly mean? Griffin. There are 3 different versions of this. There is resonance, right? So you could also draw it like this. Or you could draw it like this. Now, the truth is that it's somewhere in between all these things. Each bond is not 2 singles and a double. They're about 1 1/3 each. All right. So they'll be a little bit stronger than a single bond and a little bit shorter than a single bond. Okay. Try the next 2 on your own, or not on at your tables. You can talk to each other. I'll leave this up for a second. No, don't even worry about things happening. Once you think through things, perfect. That was exactly what I wanted to see. Okay, so NH4 plus will look like this. And the positive formal charge is on the N. Right. Now this one I'm going to cheat. So a CH3 group is called a methyl group. So instead of writing all the C's and H's out together, I'm just going to call it Me for methyl. So you'll have S, methyl, 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 and then 2 electrons. So where would the positive formal charge be? On the S in the middle. All right. So I'm not going to belabor these because you're going to get a lot of practice on the problem set in doing Lewis structures. One of the things we're really focused on this year is continuing to bring Lewis structures throughout our curriculum. Because this is the beginning of the year, right? Last year when it got to the AP practice exam, there was a Lewis structure on it, probably multiple Lewis structures, but there was one that I remember specifically that so many of my students messed up, and it wasn't one that was particularly difficult. But I think because we hadn't thought about it much since October, it was far in people's rearview mirror. So we're going to be doing these all year long on problem sets. We're going to keep up, going to make you do Lewis structures all the time, just so you don't forget, because this is something you're going to need for organic chemistry, and it'll help you in your future chemistry career. Really, I almost said really much. It'll really help you in your future chemistry career. All right. So there are such things. I think in honors chem you touched on these. I know in Chem 1 I never talked about these, but that's okay. We're all in this together now. There are things called octet violators, where they can have more or less than 8 valence electrons in a bonded molecule. So the major octet violator for less than 8, does anybody remember what that is? Boron. Boron is the big octet violator with having less than 8 valence electrons. And that's because boron is a nonmetal, but it's in group 3. So it only has 3 valence electrons that it can bond with. It's not super electronegative, so it's not going to pull extra electrons into its valence shell to make 8. But it still can make those 3 bonds. If we go down group 3, then they become metals. Like aluminum doesn't share electrons. Aluminum gives up its electrons. It's not electronegative, so it gives up its electrons. So boron is the major octet violator. Now, more than 8. There are a lot that can have more than 8. So just give you some examples. The ones that you're going to find the most are phosphorus and sulfur. These are the most common octet violators. That was supposed to be one of those things that nice connection. So is this why we say electrons don't want to have full valence shells? It can help explain that, like as not being magic. It's not the only reason why, because we can go to our fundamentals for that. But all right, most common, and then less common but still frequently seen are things like krypton, xenon, bromine, iodine, and a couple others. What's that? So, we're getting back to expanding our octet and no magic. Krypton and xenon are noble gases. But oh my god, they can bond. So, because they are octet violators, they can bond. The common explanation for this. What is the explanation you got for this in honors chem? And this has been historically the explanation we've given for octet violators. No, nothing? Okay. But you guys learned about the octet violators. But you never learned why. So traditionally, the way this has been taught is that we say if elements that are weakly electronegative have empty d orbitals in their valence shell, they can expand their octet from the S and P into the D, right? So phosphorus has this 3D energy level, right? It's in the 3rd energy level, so it has that 3D that it can expand into. Sulfur has that same thing. In its valence level, it has this 3D that it can expand into. Krypton, xenon have the 4D and 5D that they can expand into. That might be what your I say your textbook. I haven't even given them out. Like, if you want them, you can have them, but pretty not very valuable. So scientists are torn. They don't really think that's actually what's happening. And it's not expanding into that energy level necessarily, but it's just the fact that phosphorus and sulfur can still hold on and expand their octets a little bit. All right. So again, the traditional thing is that it expands to fill the d orbitals, but scientists are not particularly sure about that one. Just know that there are elements that can expand beyond 8 valence electrons. And what does that look like? So what do Lewis structures look like for octet violators? Well, BH3, B, and then what do you think it looks like? Just 3 H's, right? There's only 6 valence electrons to go around, so you get this. No lone pair, no octet. You have an octet violator. Now, NO. Try to do a Lewis structure for NO. Thomas said no. Thomas is on fire today. All right, who's got an idea of how to do no? Edward. N just is missing 1 electron. It's missing an electron in its valence shell. This has a really fun name, and it's one you've probably actually heard about in like health food things. Yeah, as Ben said, it's a free radical. Most free radicals tend to be reactive. They talk about free radicals in your body causing cancer. The reason this would potentially cause cancer is this electron here, the one that's unpaired, is pretty reactive, right? So if it's reactive, if you have free radicals in your body, they may react with, let's say, your DNA or different parts of your cell and cause damage. So free radicals can cause cancer. This happens a lot. Free radical chemistry happens a lot at high energy chemistry. So like in the upper atmosphere, free radical chemistry happens a lot. We are not going to talk about it. Right. Yeah. Upper atmosphere, the question was upper atmosphere is high energy. Upper atmosphere has a lot of energy because you have the electromagnetic radiation from the sun that's not blocked out yet. So you have the ultraviolet rays that, and even X-rays and gamma, I think there are some level of those as well. So you can have higher energy chemistry higher in the atmosphere. Okay, so we're not going to talk a lot about octet violators that are too small. We are going to talk a lot about octet violators that are too big. So we have a nice stable PF3 that adheres to all of our rules. We have nice, everybody's got a nice full octet. And then it reacts with fluorine gas. Now, fluorine gas is kind of pissed off. Fluorine gas is pissed off because both fluorine atoms are wicked electronegative and they're forced to share their electrons with each other. But they'd much rather share it with someone who's weak. All right? So this fluorine gas comes in contact with PF3 and says, hey, phosphorus, you're a wimp. I'm going to take those shared electrons from you. Or I'm going to force you to share your electrons with me. All right? So what happens here is this lone pair splits. So F is so electronegative it can force phosphorus to split its lone pair. And what we get is this. So many dots. All right, we get this. So phosphorus can actually bond with fluorine 5 times. And because I love doing this sort of grammar, I have already lectured about the shape of this, but you will not have watched it yet because it takes place after this lecture. I've done it already, but chronologically it's later. So you'll see in lecture 5.2 that we'll talk about the shape of PF5. All right. So the next reaction that you have is between SF2 and F2. Try to do the Lewis dot structure for SF4 when you're ready. So while you guys are doing that, I'll draw SF2 and F2. All right. Anybody have any ideas? What does SF4 look like? Yeah, Wesley. So many dots, but you are absolutely correct. And then you tend to put the other pair of electrons to the top left or the top right, but it doesn't really matter. All right, then SF6 does the same thing. It just splits up this last lone pair. So you're going to get this now. Now, this only happens with extremely electronegative atoms. So really, F is the one that can cause things to expand its octet the most. Oxygen can also cause things to expand its octet. These very highly electronegative atoms can force phosphorus, sulfur, bromine, krypton, etc. to share and break apart the lone pairs. Okay. Does anybody need me to wait? Yeah. Okay. So should I break the octet? The curious case of oxyanions. Now you can see that some of the references in these slides, some of these slides are like many, many years old. Did anybody see The Curious Case of Benjamin Button? Yeah, it's a really good movie, but it's how many years old now? It's probably like 8 or 10 years old. It's a bit old. It's where he ate. Maybe 6? Okay. All right, it's about 6 years old. But so some of the references are a little bit dated, but that's okay. Draw the Lewis structure that you think is the Lewis structure for PO4 3-. So I will say that there are 2 ways to draw this. So if you've drawn it one way, see if you can draw it the other. Okay, so because we only have a couple minutes left, and I want to get through some of this. As I walked around, I saw almost everybody had it one way. Ben, you had it a different way than most people. You had the textbook way. How did you draw it initially? Okay, give me the first one. Okay, so you could do it that way. You could do it this way. So I guess there's three ways, which I saw this group also had. I thought you had one slightly different than that. So this would have a 3 minus formal charge here, and you're really breaking the hell out of the octet on this one, because you're saying phosphorus can have 2, 4, 6, 8, 16 valence electrons. So this one, not so good. Most people had this. Which satisfies the octet, satisfies your 32 valence electrons. The way most textbooks have it is this. That is the way most textbooks have it, with an expanded octet around phosphorus. Now, yeah, if you Google PO4 3 minus, Lewis structure, you'll probably get this one. However, more and more data is showing that the correct one is this, and that this is not supported by data. Now, why have textbooks done this forever then? Normally, the first rule of drawing Lewis structures is you want to minimize formal charge. So the formal charge on this is I only have 3 formal charges, summing up to -3. On this, watch this. 1, 2, 3, 4, 5. I have a lot more formal charges on the one that didn't break the octet than the one that did. So, how are we going to know which to use? We are going to follow some guidelines. And those guidelines are found on the next slide, which you still have 2 minutes to get to. I'm a stickler for time, so I will keep you every second that I have you. So those of you at home, you can just read the next slide. All right. So when there are multiple possible structures to consider, use these guidelines. Structures that follow the octet rule are generally more stable than those that don't. So keep the octet whenever you can. Don't break it unless you have to. Structures with lower or 0 formal charges are generally more stable, which is why there's some conflict between these two structures. Here on the left, you have a lot more formal charges. On the right, you have a broken octet. So generally, you don't want to break the octet. Structures with formal charges prefer to have formal positive form. I'm just going to write the word in here. On less electronegative atoms and negative formal charges on more electronegative atoms. So if you have to place formal charges, place the negatives on things like oxygen, right, that have a lot high electronegativity. Place the positives on things like carbon that have a low electronegativity, or phosphorus or sulfur. There are exceptions to this, but these are good guidelines. Thank you for sticking with me. We have about 10 more minutes to do on Friday, and then we'll be done with Lecture 5, and we can start on the homework and stuff.